So here is the generic form of the kind of differential equation I want to introduce in this video, and it's called a first order linear equation. And sometimes a first order linear differential equation can be solved with separation of variables, which would mean it could be first order linear and separable at the same time, but sometimes it can't. And for the purposes of this video, since I've already gone over separation of variables, I'm going to go over treating a differential equation as a first order linear and how to solve it that way. So here I have this differential equation, dy dx plus p of x times y equals q of x. And these are all just functions of x, single variable functions. And you have this p of x is being multiplied by y. And also dy dx, the first derivative, which makes this a first order differential equation. Now, before I really dig deeper into the methods of solving this, I need to introduce a few topics. I know I've said a lot that ordinary differential equations is based on single variable calculus, but there are a few of the definitions come from multivariable calculus, and multivariable calculus really is just an extension of single variable calculus. So if I have a function y of x, I can take the derivative of that function y of x, and I would get dy dx. But with a multivariable function, it's really not that black and white. So if I have a function, say f of x, y, I can't take the derivative of the function f of x, y because it's not a single variable function, but what I can do is I can take partial derivatives of the function with respect to the independent variables. So for the sakes of problem solving and application, and for our purposes here in ordinary differential equations, a partial derivative is simply it's the derivative with respect to only one of the variables, so all the other variables are held constant. So when you take a partial derivative of a function f of x, y, if you're taking, let's say, the partial f with respect to x, you simply hold all your terms of y constant and you use the same exact differentiation rules that you would normally use. Or if you took partial f with respect to y, you would do the same thing with x. You would hold x constant and you would differentiate with respect to y using the same standard differentiation rules taught in this single variable Calc 1. So, with that being said, if the closest thing I can do to taking a derivative of a function f of x, y, if I wanted to get the derivative of that, I could define this function f of x, y of x. And if I wanted to take, say, df dx, I could say df dx equals partial f with respect to x plus partial f with respect to y dy dx. And this is done with implicit differentiation. I differentiated implicitly because I had a function of y, so I had to multiply it by dy dx. And because I also, the f, I just had to take the partial with respect to x using the standard rules that we already know, which would make this really the same thing as saying dy dx. And so the total differential of a function would be equal to df equals partial f with respect to x dx plus partial f with respect to y times dy. This is what a total differential is. So here I have this thing that I defined in the last slide, a total differential. And why is this important? The reason why this is important is because we use what is called an integrating factor when we solve a first order linear differential equation. we use what's called an integrating factor to turn the left-hand side of the differential equation into the total differential of a function. And by having that total differential of a function, it makes integrating really easy, which is why it's called an integrating factor. So let's actually go over the problem-solving method, which I'll do in the next slide. So here I've got a first-order linear differential equation in its generic form, and I'm going to utilize the integrating factor method to solve this. So the first thing I'm going to do is I'm going to multiply out my dx. So that leaves me with dy, we fix that y there, dy plus p of x times y dx equals q of x dx. And so because I've got dy's and dx's, it's not exactly feasible for me to just integrate both sides like we would with a separable first order differential equation. But on the other hand, I'm going to use the integrating factor, and the integrating factor is going to be my exponential function to the power of the integral of my function p of x with respect to x. And when I multiply everything by that integrating factor, I will get on the left hand side a total differential. So now I have e to the power of this integral times dy plus e to the power of this integral again times the function p of x times y times dx equals e to the integral times q of x dx. And what we have here on the left hand side is a total differential. This is the total differential of e to the, this total differential of the integrating factor times y, and that's equal to this single variable function e to the integrating factor dx times q of x dx. And at this point, both sides can be easily integrated, although since this is written in a very generic fashion, there's limits to all that I could show here. But consider what I am about to box in green. Why is this a total differential, you might ask? And the reason why this is a total differential is because if f of xy equals e to the, or equals the integrating factor times y, then if I took partial f with respect to x, or if I took partial f with respect to y times dy, I would treat the y constant, and then the integrating factor would be, or I'd treat the integrating factor constant, and then I would take the derivative with respect to y, which would be 1. So there I get the integrating factor times dy, plus, and then if I took partial f with respect to x times dx, I would take the derivative of the integrating factor with respect to x and treat the y constant, and after taking the derivative of the integrating factor with respect to x, I would use the chain rule and take the derivative of what my exponential function, what e is being raised to, which the derivative of an integral would just be the function p of x. So that's where I get that. So both sides can be easily integrated at this point. So this is what my first order linear differential equation in its very generic form has come down to. And if I wanted to integrate both sides, I said this is already very easy. Well, the integral of a differential is just the function, and this right hand side of the equal sign, I really can't simplify this because it's so generic and theoretical that it is what it is, but it would just be the integral of all of this with respect to x. And so after simplifying everything, I would get that y is equal to e to the minus p of x, or the inverse of the integrating factor, times this integral right here, e to the p of x dx, well, the integrating factor times q of x dx. So this is what would solve any first order linear differential equation if you just plug it into this simple formula, really. And that's if it's linear in x. If it's linear in y, everything that I've shown here, the same concepts could be applied with respect to y being the independent variable, and then you'd end up with x as a function of y. But that really sums up everything in terms of the theory behind a first order linear differential equation.